My name is Dr. Shobhusha Chishen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For Computer Science and IT, bouquet is something. For Mechanical, Civil, it is different. For Electrical, Electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the Computer Science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Hello and welcome to the 16th class of my course on Physics 2. Hello, I hope all of you are going very well. Everything is okay at your end. So far the journey has been very fascinating. So far the journey has been very nice. So far the journey has been very nice and smooth and good. So I thank you for that. I have taken already 15 classes. There I covered entire quantum mechanics too. We started from the very basic concept of what is called a wave function until the concept of operators, and finally all the applications of Schrodinger's idea in variety of physical problem. It may be the problem of electrons moving in a metal. It may be the problem of how electrons or holes moving in a junction diode, or it may be the problem of how a particle is moving in restricted to move in 3D. The concept of degenerate states, which are needed in explanation of the semiconductor actions, which are also connected in the, you will find it the application in nanomaterial called quantum dots. Okay, so many wonderful applications are there. Now what shall I do actually? We'll now apply our quantum ideas, particularly the concept of operator, the superposition principle in general, for the development of a new branch of quantum technologies, I should say, which is called quantum computation. The heart of quantum computation is quantum mechanics and the superposition principle. So today now I'll start unfolding the various facets, various new idea that is inherent with this within the study of quantum computation. Quantum computation is unique. Quantum computation is new. Quantum computation is, it has got a tremendous potential because this is the future of computation. The computer, or you know now, that is the computation or the computer based on the Boolean algebra or Boolean logic. Okay, Boolean algebra means there exist only two numbers, 0 and 1. Apart from 0 and 1, there is no other number. Okay, so anything you do in Boolean logic, you have to, it will be addition of 0 and 1, subtraction of 0 and 1, multiplication of 0 and 1. They either produces one of them. Okay, so it may be any arithmetic and logical operation leads to only combinations of zeros and ones. Whatsoever may be the logic gates you are using, and they have got this Boolean algebra based all the arithmetic and logical operation. They rely on the these combinations of zeros and ones. Now, what you do in quantum computation, you get out of the box of zeros one. Okay, they are the basic and fundamentals are based on quantum ideas, based on the principles of quantum mechanics. Their numbers may be in normal binary system, we realize 0 and 1 through voltage value in reality. Here in quantum computation, we will be realizing 0 and 1 maybe through quantum mechanical state of electron. Okay, that may be spin up and spin down state. So some beautiful things are waiting for you, and I can assure it is a future of computation. Because you have learned quantum mechanics now, quantum mechanics 2 particularly, all the techniques of operator, etc. you know. So basically, we are now in the right position to apply all those ideas for the development of quantum computation. So let us explore quantum computation. I assure you, it is going to be a very nice journey because you, as a IT or CSE professional, you are somewhere or the other. The future is quantum. Okay, the future of computation is quantum computation. So how it works? Some of you may be working in Google. Google has come up with its quantum computer last year. So basically, many new, the entire physics and electronics are now focusing on this on the nano aspect of it. Okay, nano devices, the concurrent changes in the computational part, that is quantum computation. So that is what we are doing now. Okay, if you do higher study, you realize these things are so beautiful. So in our course, we'll try to make the foundation of that. Okay, so this is the 16th class in a row, in as I mentioned 2 minutes back, and this is myself obviously. And if you look at the quantum mechanics, also it has got two major approaches. One is called the approach of Schrödinger. Essentially, so far, whatever with the quantum mechanics we studied, this is based on the ideas of Schrödinger. I actually compared in this way. Quantum mechanics begins with Schrödinger, Newtonian mechanics begins with, and the classical mechanics begins with Newton, like that. So similarly, our approach was merely Schrödinger equation approach. We solved Schrödinger equation in solution of the problems. We got shy and we did many things. But apart from that, there is an approach called Heisenberg approach, which is something new. But the origin is lying somewhere else in the mathematics. Okay, it is more like operator method. Okay, it is the operator approach. So the same wave function will be interpreted or represented differently in these two approaches. Wave function, as you know from postulates of quantum mechanics, and I've been shouting almost every class before this, that wave function is everything. It is a fundamental, it's a basic variable of this quantum mechanics. Now this wave function is represented by mathematical function, okay, in the Schrödinger approach. The same wave function will be vector, state vector in the in this approach, in this new approach. There is a Heisenberg approach. So altogether different background. Now when you psi, the wave function was just a mathematical function in Schrödinger approach. Now it's a vector. It is a vector that is called a state vector in this new approach. Okay, now
all of you know how a function looks like in Schrodinger equation. It may be sine function, it may be cos function, it will be e to the power I function. So you had some earlier knowledge, preliminary mathematical background of how mathematical functions are represented with. But now in the Heisenberg approach, you are getting a new domain of mathematics. We are using a vector, state vector psi to represent the wave nature of matter. So matter is manifested not by a function in this approach. It is represented by a vector, state vector. And you know, in quantum computation, this new method, the second approach, that is an approach based on the Heisenberg, or approach where you are representing a state vector to represent the matter, that is used. So altogether, physics is simple. It's a microscopic domain you are talking about. So you have to rely on mathematics more. But the mathematical technique that if you followed in Schrodinger approach, that is to solve differential equation, get the function, we could not able to use the same technique. Okay, here the technique is different. What is that technique? Technique is the technique of vector, state vector. We will use a vector to represent the psi, represent the wave function, and that representation is called a Kate vector representation. So what we need now, we need a profound knowledge, a new mathematical background of this state vectors. So what shall I do now? I will form that mathematical background. The same 0 and 1 will come off and on. Earlier it was off and on in classical computation. Now in quantum computation we will get 0 and 1, but now they will be quantum mechanical wave function or a state vector. So what is a state vector? So that is the most important point actually, and ultimately it is going to represent that 0 and 1. So how do you represent that 0 and 1? It may not be the voltage value, something else, because ultimately we are now using a vector to represent the wave nature of the matter. That vector will replicate the matter. So how it is happening? To understand that, we need to explore that basic mathematics of vectors. Now state vector is actually studied through linear vector space. Now a state vector is an element of linear vector space. So what is a linear vector space? Linear vector space is a set of elements, as I have written there, psi, phi, chi, zeta, theta. They can make a state vector. Only thing is that they have to satisfy some property. They have to satisfy some relationship. One classical example is the Cartesian coordinate system. In Cartesian system, I've got only 3 vectors, I, j, k. So this is a linear vector space, and the corresponding vectors may be ket I, ket j, and ket k, I have written here. But they can only make a vector space, as you mentioned in the basic definition of vector space. They have to satisfy some physical properties. Some properties they have to satisfy. So what are those properties? We'll discuss them. Okay, but before that, few more mathematical understanding need to be illustrated and clarified. So that is what shall I do first. Okay, so it's all mathematics now. So let us realize it. Okay. Now first point is that what is a linear vector space? A linear vector space is a set of elements. It is a set of elements, psi, phi, okay, psi, phi, chi, zeta, theta. These are the set of elements. Now these elements have to satisfy some properties. Okay, it is a set of elements which satisfy some properties. They make a linear vector space, and these elements are called state vectors. So these are the state vectors. So there are 5 elements. So it's a linear vector space of dimensionality 5, and I've got psi, phi, chi, zeta, theta as a state vector. Now one classical example is obviously the Cartesian coordinate system, where there are 3 vectors are there, ket I, ket j, and ket k. So what is the dimensionality of 3-dimensional space? 3D. So you see number of elements equal to the dimensionality of this space. In 3D I have got 3 vectors, ket I, ket j, and ket k. Number of elements equal to the dimensionality of the vector space. Now come to the case. So what is ket I? Ket I is basically, it has 1, 0, 0. Its length is unity. Ket j, length is unity in y direction, and ket k means length is unity in the z direction. So I is like 1, 0, 0 according to this coordinate system. J is like 0, 1, 0. K is like 0, 0, 1. So that means I can represent this 1, 0, 0 of I as a matrix, as a 3 into 1 column matrix. I can represent this 0, 1, 0, this J as a 0, 1, 0, 3 into 1 column matrix, Again, I can represent this K also as a column matrix, that is 0, 0, 1. Okay, so what I am doing, every element is expressed as a matrix. So this is a matrix representation of every element, and information is that number of matrix element equal to the dimensionality of this space. Number of matrix elements equal to dimension of the space. So in 3D there are only 3 elements. So what is a state vector and how do you get it through Cartesian system? That I tried to tell you. So what shall I do now more? You see, these elements have to now satisfy some properties. What are those properties it has to satisfy? First, some properties that you studied in your higher algebra courses, similar properties it has to satisfy. Okay. So what are those properties? First is the property of additive property. Suppose this is my linear vector space represented by V tilde, and these are my elements psi, phi, chi, zeta, theta. First property it has to satisfy, if we add any two elements psi and phi, the final value will belong to the same vector space. For example, if I try to realize through Cartesian system, suppose psi is I and phi is j. So if you add it, this is like 1, 0, 0, and j is like 0, 1, 0. So it is like 1, 1, 0. Okay. So this is obviously an element of the same vector space. Okay, and you see this is 1, 0, 0. This is 0, 1, 0. Okay, and this 1, 1, 0, okay, is this vector. Okay, it belongs to the same vector space. Very simple. Now next property of addition is this law, additive law. Suppose I have got 3 vectors psi, phi and chi. So if I can add them like this way, suppose first phi and chi added up, then you add psi with that, or it is equal to first you add psi and phi and then with chi. Okay, it will give the same result. So let me explain that through the example of Cartesian system. Suppose psi is the vector I, phi is the vector j, and chi is the vector k. So if you use this idea from here, psi plus phi plus chi psi is 1, 0, 0, phi is 0, 1, 0, and chi is 0, 0, 1. And here also same thing, 1, 0, 0 plus 0, 1, 0. Outside is these two are inside as third bracket. Okay, and you can understand here also if I do the addition I will get 1, 1, 1, and if I do the addition here also I will get the same thing, and it belongs to the same vector space because this is 1, this is 1, this is also 1. Okay, so 1, 1, 1 means a vector having is like this. Okay, slightly projected up. Okay, it is like this. So this is the additive law. Now the concept of field. Field means now the concept of field is connected to the concept of multiplication. A field means a set of numbers. Suppose I've got few numbers A, B, C, D, up E, F up to N. So they makes a field F. F is the field. Now if these numbers are real number 1, 2, 3, 4 up to N, that makes a real field. And if they're complex number 1i, 2i, 3i, 4i up to Ni, they makes a complex field. Okay. This is making a complex field. Okay, this makes a complex field like this, C to the power n. Now the property is that, so these are basically scalars, y, 2i, these are all scalar, these are not vectors. So now when I talk about the scalar multiplication of the state vector, First, so these scalars, suppose A is the scalar, it is coming from a field. So it is contributed by a field. Suppose, for example, A is equal to 3. A is equal to 3. Now, if I suppose psi is equal to I vector plus phi is equal to j vector. So suppose psi is equal to I vector. So if I do A psi, so that means I am doing this much 3, 1, 0, 0. So this is nothing but 3, 0, 0 vector. And you see 3, this is 1, 0, 0. So this is my I. So this is basically 3, 0, 0 vector. 3 times 1, 0, 0, the longer one. So obviously, if I call it phi, it belongs to the same vector space. Now another idea may be like this much. Another idea may be like this much. Associative law of multiplication. Suppose I have got two numbers A and B. If I multiply that to a vector psi, so that resultant will belong to the same vector space.
ওই যেন বাবা আমাদের বাইক মা যেন একটা বাস করতে দিয়েছে যেটা তুমি এনে দিয়েছিলে অনেকদিন আগে আমি চাই একটা একটা ব্লু বাস আর একটা একটা ট্রেন একটা গ্রে ট্রেন সেটা মা খুঁজে দিচ্ছে না
Now suppose I do calculate this A B psi. So this will be as good as 2 into 3 into I vector if I consider psi as I. So you can understand it is 6, 1, 0, 0. This is nothing but 6, 0, 0. 6, 0, 0 means it's a long vector. If this is I, so this is your 6, 0, 0. You may call it phi. So obviously it is falling into the same coordinate system. Okay, it belongs to the same vector space, that means. So these are the property of multiplication. Now, this has been the property of scalar multiplication. Now let me talk about the property of vector multiplication. So please try to put all attention in the vector multiplication. Suppose I am trying to add two vectors, psi and phi. So I want to know what is the result of these two vectors. And let us understand that through Cartesian system. Suppose I is psi and j vector is phi. So if you do the multiplication, it is I into j. I want to know what is the value. So if I do it, it is like this much. I means 1, 0, 0 vector and j means 0, 1, 0 vector. This is the multiplication. Now can you multiply? The answer is that I can't multiply. Why? Because the left hand for matrix multiplication, you know, this left hand side matrix is not good enough. Okay, with you cannot multiply in the usual way of matrix multiplication. You know, you cannot multiply this. You can multiply this if you how do you multiply then? If you convert this vector, this matrix into this form, okay, then you see multiplication is possible. Now you can multiply. So then what you are doing, it seems that I am taking transpose of this initial matrix. So basically what you have to take adjoint of the matrix. If you take adjoint, then you see this is becoming like this. Now question is that what is adjoint vector? Adjoint of one or two vector. Suppose what is adjoint? Suppose I have got a vector is like this much 1, 2, 3, 4 I. Okay, this is the vector or this is a matrix. Now adjoint means it is represented by a simple a dagger. This is called adjoint of the matrix C. First you have to take transpose, then followed by complex conjugation. So if you take transpose, it is like 1, 3, 2, 4i. Now if we do the complex conjugation, now this 4 will become minus 4i. So this is called you are taking the adjoint of the matrix. So here also, if my matrix is like 1, 0, 0, 1, 0, 0, so if I take adjoint, it will become a row matrix. And because there is no I big business, so you cannot understand the conjugation process. So if you have to multiply two vectors, that means the left hand side vector has to be a called row matrix. Now the problem is that this new one, this new vector is not a member of the 3D space, because in 3D there may be only 3 vectors. In 3D there are only 3 vectors are there. What are those vectors? One of them is I, which is a column matrix 1 0 0. The other one is J, which is also a column matrix 0 1 0, and the other one is K, which is also a column matrix 0 0 1. So this will be 3 elements. I told you that number of matrix element equal to the number of elements equal to the dimensionality of the space, equal to dimension of the space. So in 3D, I have got 3 elements, that is I, Kt, Kj, and Kt. Now, this new matrix that is being generated here, it is not a column matrix, it's a row matrix. So obviously, it's not a member of the same vector space. It is coming from some other space. So actually, if you just try to realize it, that in Cartesian space, I have got 3 matrices. For Kt, which I represented, say I vector, J vector, and K vector, 3 K vectors are there. These are the elements of Cartesian space. Now I is 1 0 0, J is 0 1 0, and K is 0 0 1. Now what you have to do, you have to take adjoint of this matrix. If you take adjoint of these vectors, then by taking adjoint, what they will happen? This is becoming 1 0 0, this is become 0 1 0, and this becomes 0 0 1. Now these 3 vectors are not a member of 3D Cartesian space. Because in 3D there may be only 3 vectors, 3 matrices. So where from they are coming? These matrices, these are actually coming, okay, all of them are member of dual space of 3D Cartesian space. So this is, suppose this is its adjoint. So these 2 vectors, so this ijk is forming a linear vector space whose matrix representation is this 3 column matrices. Similarly, these row matrices are now, they will form dual space of linear vector space of Cartesian space, 3D Cartesian space. So in dual space, this will be the matrix element. These are called, and these are called dual of each other. Okay, so this will be the matrix elements for the dual space. So if you don't understand, I show you just again, then you will realize that what is meant by the dual space. See, in Cartesian system, therefore, you see, this is my Cartesian system. I know there are 3 elements. One of them is I, another is J, another is K, which are represented by 3 K vectors. And these are 3 column matrices. Okay. Now the idea is that they are represented by 3 column matrices. As you can see there, 3 column matrices are representing them. Now there exists a dual of this initial space. Okay, there exists a dual space of this initial vector space. Okay. Now in the dual space, what are the elements? These elements will be the adjoint of the initial matrices. So this will be 1 0 0, 0 1 0, and 0 0 1. Now this is making the dual space of the 3-dimensional Cartesian space. And these elements are actually dual of each other. They are actually dual of each other. And these elements obviously does not belong to the 3-dimensional Cartesian space. And they are represented, this dual space representation is that they are called bra vector, bra I, bra j, and bra k. The bra vectors are represented by row matrices. These are 1 into 3 row matrices. So idea is that if you have to take the product, okay, you cannot take the product of 2 vectors of same space. Okay. So what we are talking about, we are talking about the product of the 2 vectors. Okay. We have been talking about taking the product of the 2 vectors. I and j. So what I have to do? I have to take adjoint of I. If you take adjoint of I, this is becoming like 1 0 0. Now this is I am calling bra of I. This is called kth vector I. This is called bra vector of I. Now there is no change in the right hand side because this was 0 1 0. You can now do the multiplication. So this is now becoming the j vector. So this is in the kth formation. So if you do multiplication, you are actually forming a bracket. Okay, and what is the result of this multiplication? 1 into 0 is 0, 0 0 into 1 is, so it's a 0 0 0 matrix, and try to realize it's a number. Okay, sorry, it's not a matrix. The result of this multiplication will be 1 into 0 plus 0 into 1, 0 into 0, and you see it's a scalar. So this type of products are called scalar product or inner product. So if you are doing bracket formation, bracket notation, you are making inner product of vectors. And because final outcome is a scalar quantity, this is also called scalar product of the vectors. So we do, what is the idea? For inner product to take, so if you have to take inner product, of the two vectors, if one of the vector is phi, the other vector has to be an adjoint. Okay, this is coming from the initial space. Now the left hand side vector has to be coming from the dual space. So if these are the elements, say psi, phi, chi, etc., then there exists a dual space, bra psi, bra phi, bra chi. So left hand side vector, if your intention is to take the product of psi with phi, then psi should be dual in nature. So basically you have to do this type of product. Okay, so this is a bracket notation that you are using. Suppose just now we did ij, and it will be ending up with a scalar quantity. Now likewise we can take the two vector of, so left hand side vector has to be, they are not the element members of same space. Okay, they are the members of two dual space of each other. Now another important and interesting story is that suppose you want to take the product of two vector of same space. If you wish to take the product of two vectors of same space, then what would happen? If you try to take the product of two vectors of same space, then this thing would happen. Okay, please see, let me just take the product. Okay, this is called outer product. Suppose one of the vector is I, the other vector is again j. Now I am trying to take the product of same space. So this is the notation, cross with a circle. This is the notation of the outer product. Outer product of this taken for the two vector of same space. Then the technique is that you have to represent the vector I in its matrix notation 1 0 0. I'm using it in 0 matrix notation. So if you do the multiplication, you'll get a matrix like this: 1 into 0, 1 into 1, 1 into 0. This is the first. Next case you will get this much: 0 into 0. Okay, 0 into 0. After that 0 into 1. After that 0 into 0. Now next case would be this much. This will be multiplied. Okay, it would be equal to 0 into 0, 0 into 1, 0 into 0. So if you look at the multiplication, it is like 1 into 0 0, 1 into 1 1, 1 into 0 0, 0 0, 0 0, all are 0. So this is a 9 into 1 matrix. So the result of this the outer product of these two vectors, okay, this is represented by this. This is ending up with a matrix like this, which has got 9 elements: 0 1 0, 0 0 0, 0 0 0. So it is this vector obviously not a member of three-dimensional space, because it's a member of n-dimensional space. Because in 3D you know, suppose this I vector, it's a member of three-dimensional space, so there will be 3 elements. So here there are 9 elements are there. Rather, this is a member of 9-dimensional space. This quantity is actually called a tensor, and this product is also called tensor product. So if you take product of 2 vector of same space, you are doing the tensor product, and earlier one you are doing the scalar product. Okay, so you see this is the symbol of outer product of tensor product. Okay, understand? So you are ending up with the vector of higher dimension. So now these are all about the inner product and outer product. So if I make a summary of the two discussion, it is like this, that if you take the side by side, if I put for inner product and the outer product, for inner product, suppose I want to multiply these two vector I and j, this is inner product notation, and for outer product notation, this is my symbol. Now for inner product, this side it has to be, you have to take dual vector of it. It has to be a bra vector, and this is a j vector. This is a ket vector. But here you can take the product of two ket vectors, and in the end result is a scalar. Here end result is that you will end up with a tensor, and that is an element of a higher dimensional space. Okay, that is an element of a higher dimensional space. Okay, so that is the story all about the product. Now, so far I think I have introduced a bit about the various types of basics of the basic state vectors. So let me get back to the PowerPoint a bit. So I told you these few issues. Okay, through example I have introduced Cartesian system, and now these are the properties, okay, that the vectors have to satisfy. The concept of field I have written, the scalar field, the real field, complex field, and how do you take the product of inner product and outer product. So next class we'll begin our journey towards basis vector, and we move into a new space actually called Hilbert space, and there our favorite quantum bit is residing. So we'll identify that, but that is the next video lecture. Thank you.